All right, this is it's actually section 7.1. Not sure why I called it section 3 here, but it's the area of a region between two curves. So, the area of a region between two curves. What I'm saying is I have a curve and another curve, and I just want the area in between those. The idea is that we take the area underneath the top curve minus the area that's underneath the bottom curve, and that leaves us just the area between them that we want. We also talk about a representative rectangle. A representative rectangle is essentially just a rectangle that we're going to make super, super small. And we're going to think about it for the area. Delta x will be very, very, very small. The height of it, though, will be the top function's value minus the bottom function's value. That's f of x minus g of x, whatever that x is. And we add up all the areas of those little rectangles until we get to the area. So the area between two curves. F and g are both continuous on the interval, and g of x is less than or equal to f of x for everything in that interval. Basically, this just means g of x is the lower function, f of x is the upper. The area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is the definite integral from a to b of f of x minus g of x dx. Top minus bottom. There we go. Also note that it does not matter if they lie above or below the x-axis. It's going to work out exactly the same no matter what. So let's find the area of the region bounded by y equals x squared plus 2, y equals negative x between 0 and 1. First thing to think about is which function is on top. Now I've given you the picture here so you can tell that f of x is on top. Well, never mind, they're not called f of x. But x squared plus 2 is the top. And negative x is the bottom. Our interval is from 0 to 1. So to find the area, we take the definite integral from 0 to 1 of the top minus the bottom. So the top is x squared plus 2 minus the bottom is negative x dx. I'll combine it a little and simplify before we do our actual integration. So 0 to 1 of x squared plus x plus 2 dx. And now it's just what we've been doing. So this definite integral is 1/3 x cubed plus 1/2 x squared plus 2x evaluated from 0 to 1. And remember, we plug in the 1. So I get 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1 minus, if I plug in 0, I'm going to get 0. So my answer is going to be 1/3 plus 1/2 plus 2. Let's get common denominators, right? 2 6 plus 3 6 plus 12 6 is 17 sixths. There's our area, 17 sixths. Another challenge we're going to have is to find the area of a region between intersecting curves. It's exactly the same as what we just did, but there's one more step. First, you have to calculate the points of intersection of the graphs. If the graphs intersect more than twice, we're going to have to use multiple integrals because they probably switch which function is on the top and the bottom. But it's going to be where they intersect to the next intersection, top minus bottom. So let's find the area of the region bounded by these two graphs. Well, the first step is where do they intersect? So where does 2 minus x squared equal x? All right, quadratic equation, let's add that x squared over and subtract the 2. 0 equals x squared plus x minus 2. I'll factor that. I get x plus 2, x minus 1. So they intersect at x equals negative 2 and x equals 1. So we are going to take, the area is going to be the integral from negative 2 to 1. Now we have to decide which function's on the top and the bottom. To do that, pick some number in the interval. I like x equals 0. If I plug that into my two functions, f of 0 is 2, g of 0 is 0, 2 is bigger than 0, which means f of x is the top. So we'll take f of x, which is 2 minus x squared, minus g of x, which is x, dx. Now I don't even need to rewrite this. I can just go straight for my integration. I have 2x minus 1/3 x cubed minus 1/2 x squared, evaluated from -2 to 1. And that will be, when I plug in 1, I get 2 minus 1/3 minus 1/2, minus, when I plug in -2, I have -4 plus 8/3 minus 4/2. Since I'm doing this without a calculator, I had to do a little bit more work. Let's see, I have 12/6 minus 2/6 minus 3/6 minus, let's see, that's actually 2. So -6 is 18/3 plus 8/3. So I have 7/6 minus plus 10/3, which is 7/6 plus 26, which is 27/6, and simplifies to 9/2. There we go. So most of that was just simplifying fractions, right? All right, so these sine and cosine graphs intersect infinitely many times, right? Over and over and over, bounding several regions that have the same exact areas. So let's find the area of one of those regions. So we want to know, where does sine of x equal cosine of x? Well, that happens at pi over 4. And then again at 5 pi over 4. Then 9 pi over 4. 13 pi over 4, on and on. But we know these are the first two intersections, so there's my integral. The area will be the integral from pi over 4 to 5 pi over 4. We have to decide which function's on top. The sine of, let's see, let's pick a number in there, pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Sine's the top, so I'll take sine of x minus cosine of x dx. I integrate. The antiderivative of sine is negative cosine, and the antiderivative of cosine is sine, from pi over 4 to 5 pi over 4. I'll plug in 5 pi over 4, negative cosine of 5 pi over 4, minus sine of 5 pi over 4, minus negative cosine of pi over 4, minus the sine of pi over 4. All right. Cosine of 5 pi over 4 is negative square root 2 over 2. Stick a negative on the front, we have square root 2 over 2. Sine of 5 pi over 4 is negative square root 2 over 2. That makes it positive because of that minus in the front. Minus, hey look, it's going to be very similar. Cosine of pi over 4 is positive, so that's going to be negative square root 2 over 2. Sine of pi over 4 is also positive, so there we go. Let's change all those signs. I have 4 times square root 2 over 2, which is 2 square root 2. There's my area, and then it's repeated, obviously, over and over. Let's find the area of the region between these two graphs. So step 1 is figure out where they intersect. Set them equal to each other. 3x cubed minus x squared minus 10x equals negative x squared plus 2x. All right, let's get it equal to 0. So add this x squared over and subtract the 2x. I have 3x cubed minus 12x equals 0. Take out my GCF, which is 3x, leaving me x squared minus 4. All right, set each of those equal to 0. I get x equals 0, and x equals plus or minus 2. All right, now we have to choose in each interval. So let's use negative 1, and let's use positive 1. Because our intervals are going to be negative 2 to 0 and 0 to 2. All right, so f of negative 1, let's see, positive 6. G of negative 1 is negative 3, which means f is the top in that section. So this section here, f is the top. So we'll take 3x cubed minus x squared minus 10x minus negative x squared plus 2x dx. Sorry, I should have left myself more space then. All right, and same thing with positive 1. I get negative 8 for f of x, positive 1 for g of x, which means g of x is the top in that section. So here we'll take g of x minus f of x dx. We'll simplify this down a little bit and then evaluate our integrals. So I have the integral from negative 2 to 0 of 3x cubed. Let's see here. These cancel out. Negative 10x minus 2x is minus 12x dx, plus the integral from 0 to 2 of, let's just distribute that negative there. The x squareds cancel. I have 12x minus 3x cubed dx. Notice they're very, very similar. Just the positive and negative changes. So, antiderive, I have 3/4 x to the 4th power minus 6x squared, evaluated from negative 2 to 0, plus 6x squared minus 3/4 x to the 4th power from 0 to 2. All right, plug in 0, I get 0, minus, when I plug in negative 2, I get 12 minus 24. Plug in positive 2, I get 24 minus 12. Plug in 0, I get 0. All right, I have positive 12 here, positive 12 here. The final area is 24. There we go. All right, the area of the region bounded by these two graphs. Uh-oh, they're in terms of y. That's fine. We're just talking about graphs that are evaluated horizontally rather than vertically. No change. Set them equal to each other. 3 minus y squared equals y plus 1. All right, get everything on one side. So I'm going to move my y squared and my 3. 0 equals y squared plus y minus 2. So that'll be y plus 2 and y minus 1, which means they intersect at y equals negative 2 and y equals positive 1. So our integral will be negative 2 to 1. Now I decide which one's on top. I would take 0. All right, that gives me a 3 and a 1. So that means the first function is on top, minus the second one, dy this time because we're working with y's. Combine everything here to make my life a little easier. I get negative y squared minus y plus 2 dy. And my integral would be negative, or my indefinite integral, negative 1/3 y cubed minus 1/2 y squared plus 2y, evaluated from negative 2 to 1. And we get negative 1/3 minus 1/2 plus 2 minus positive 8/3 minus 4 over 2 is 2 minus 4. All right. Let's change this stuff into sixths. Negative 2/6 minus 3/6 plus 12/6 minus, we can change this into thirds. 8/3 minus 6/3 minus 12/3. I get 7/6 minus negative 10/3, which we've definitely already added together once today. It makes 27/6 or 9/2. All right, your assignment is out of your textbook. Keep an eye for that.